Very good evening, everyone. Today we will be seeing the tutorial 3 of BT39 NPTEL course, which is named as Bioreactors. This tutorial 3 is going to help you solve the assignments of week 3, whatever the assignments are posted for week 3. We'll just have a quick overview of what we have seen in tutorial 2, and then we will be proceeding to tutorial 3. We'll just get started. Let me share my screen. Yeah, we'll just have a overview of tutorial 2 first. Whoever has missed the last class, like tutorial 2, this will help you in getting a overview of what we have seen in tutorial 2. And in the tutorial 2 that I have explained very nicely, I have given an overview of tutorial 1 as well. So whenever I'm starting a new tutorial, I'm just giving an overview or a quick explanation of what we have done in the previous week also. Okay, so we'll just see this. Which among the following is the cheapest carbon source for microbial culture? Glucose, starch, ammonia, and glycine. So out of these, we have seen that glycine is an amino acid, ammonia is a nitrogen source, and out of glucose and starch, starch is much more like available in the nature as such. So we can use any feedstock, do any chemical treatment, thermal treatment, or else like enzymatic treatment, and then whatever the treated feedstock is there, that we can use it as a carbon source for the microbial culture. So this is a kind of cheapest carbon source that can be used for microbial culturing also. For this, starch is the answer. So anyway, if we break down starch using any of these method, we are going to get glucose at the end. Okay, so that's why starch is considered as the cheapest carbon source. Question 2. When the substrate happens to limit growth, which among the following method is used for modeling the growth profile? We saw the equations for all four like last time. So Ludeking Pirate model is a product formation kinetics. Monod model gives the relationship between substrate and the specific growth rate, but not any idea about the inhibition at all. Whereas Jerusalemsky-Neronova model shows that how a product can inhibit the growth of the organism, whereas Andrews and Nyok model shows the substrate inhibition on the growth. Okay, the answer is Andrews and Nyok model. Moving to question 3, which of the following is true according to Michaelis-Menten kinetics? So Km is dependent on the enzyme concentration, Km is independent of the enzyme concentration, Vm does not vary with enzyme concentration, Vm varies with enzyme concentration. So we were seeing what is Michaelis-Menten kinetics. V is equal to Vmax, S divided by Km plus S. Here Vm corresponds to K3 into Et, whereas Km corresponds to K2 plus K3 divided by K1. So Vm varies with enzyme concentration, whereas Km is independent of enzyme concentration. B and D are the answers. So we even saw very in detail that how this derivation happens also, although sir has explained the lecture. As there is a need that we have used this equation in the previous problem in tutorial 2, I have explained this derivation also. You guys can go to tutorial 2 and then have a look at it. Moving to question 4, uncompetitive, non-competitive and competitive inhibition. So we just saw in uncompetitive inhibition, inhibitor will bind only to enzyme substrate complex, whereas non-competitive, it can bind to free enzyme as well as enzyme substrate complex also. In competitive inhibition, it can bind only to the enzyme. Okay, so accordingly the answer is A. Among the following, which are involved in the estimation of cell concentration, as we were seeing, optical cell density that we take it like OD 600, we take it very normally, whereas hemocytometer is used in mammalian cell cultures to find the like what to say in a overall cell counting, mainly hemocytometer is only being used, whereas Strifen blue, where the dead cells are like stained as blue, whereas the live cells are like intact. Okay, so Strifen blue can differentiate between your what to say your live cells as well as dead cells, whereas the previous one like optical gel density, it's the overall cell concentration. We can't differentiate between your live cells as well as dead cells. Okay, so the answers are like A, B, C. So moving to question 6, spirulina, it's a biomass in itself, whereas streptomycin, it's an antibiotic which comes in the secondary metabolite, whereas growth dependent products are primary metabolites. Okay. Define Ks in the monad model. Ks is the substrate concentration at which growth rate is half maximal. Ks is the substrate concentration at which growth rate is equal to 1. Ks is the substrate concentration at which growth rate doubles. Ks is the substrate concentration. Ks is the growth rate at which substrate concentration does not influence growth. So as this is talking that what happens when we put K is equal to S. Okay, so what happens, S and S will get cancelled, mu max divided by 2, which is nothing but K is the substrate concentration at which growth rate is half maximal. Moving on to question 8, in the monad model for growth kinetics, with the single limiting substrate, the plot of substrate concentration versus growth is linear, hyperbolic, sigmoidal, or cannot be determined. So as we cannot determine as such, we'll just try to compare the formula. This is the monad model equation. Anyway, it's not linear, that is for sure. Linear is what? Y is equal to mx, that is not here. Whereas in the rectangular hyperbolic, the equation is designed as like y is equal to ax plus ax divided by b plus x. It's rectangular hyperbolic. Coming back to question 9, where we have to find Km and Vmax, we have been given time S and like V. So what we have done, like we use line paper plot. So in this, what happens, like y is equal to mx plus c. So here y axis is 1 by v and s axis is 1 by s. We have plotted the graph, and this is the equation that we got from it. 1 by Vmax is equal to this much. So we just take in Vmax, how much ever it is, and then we substituted Vmax in Km divided by Vmax is equal to 0.4577. So the answer is Km, like D. Okay. Given the above data, what happens to the value of Vm if the enzyme concentration in the system is doubled? So we already know that Vmax is equal to K3 into ET, okay, which is nothing but Vmax is directly proportional to ET. If the ET is getting doubled, obviously Vmax will also get doubled. So the answer is value of Vmax is doubled. Okay, this is what we have seen in the last tutorial. So I was just explaining you guys what we saw in the last tutorial. Now we'll get into tutorial 3 of BT39 bioreactors course. Okay, so the question 1, an industrially important enzyme is produced from thermophilic bacteria in a bioreactor operated in batch mode. 70 liter of media was inoculated using 8 gram of cells. The lag phase was found to be 30 minutes. The maximum specific growth rate of the organism is 0.52 R inverse under the conditions maintained. Calculate the cell concentration after 9 hours of growth. Choose the answer closest to your calculated answer. Option A, 10.9 gram per liter. Option B, 12.2 gram per liter. Option C, 9.5 gram per liter. Option D, 0.9 gram per liter. Okay. So what is given, we will see first. So what they have told, we are using 8 gram of cells for 70 liter of media. Okay, so X naught, usually cell concentration should be in gram per liter. Okay, so 8 grams of cells we are adding, but in how much volume we are adding? We are going to add in 70 liter media. Okay, so 8 divided by 70, which is equal to 0.11 gram per liter. So cell concentration is always in gram per liter only. It's a concentration, right? And they have given T naught, that is the lag phase is found to be 30 minutes. Okay, and the maximum specific growth rate mu max is considered to be 0.52 R inverse. Okay, so calculate the cell concentration after 9 hours of growth. So how much amount of cells X will be there when time T is equal to 9. Okay, so we'll just see what we have to find cell concentration at after 9th hour which is x. Okay, we are considering. So we know that what is the formula? 1 by mu ln of x divided by x naught plus t naught is equal to t. Okay, so here 1 by mu is the specific growth rate, x is the cell concentration at whatever the time we are going to find, whereas your x naught, that is your initial cell concentration, that is what we have found here, 0.11 gram per liter, and T naught is the lag time, which is 30 minutes, that is equivalent to 0.5 hour, and T that we already know, that's what we are going to find, like 9 hours. At T is equal to 9 hours, we are going to find what is X. Okay, so here we have to rearrange, so I'll just try to do it. So what we want here, 1 by okay, we wanted to keep x on one side and put all the other equations on the parameters on the other side. So we'll just do it step by step. So 1 by mu ln of x divided by x naught is equal to t minus t naught. Okay, so that's what is going to happen at first. So we'll just see 1 by mu ln of x divided by x naught is equal to t minus t naught, right? Ln of, so now we'll just take it for multiplication. So what happens, ln of x divided by x naught is equal to mu into t minus t naught. Okay, so this is ln of x divided by x naught. So when ln goes on the other side, what happens? X divided by x naught is equal to e power mu into t minus t naught. So we want to find x only. X is equal to x naught e power mu t minus t naught. Okay, so we already know what is x naught. We know that it is 0.11 gram per liter, e power your mu is 0.52 R inverse, and then t minus t naught will be 9 minus 0.5, which is 8.5, right? Okay, so that's what I have also done here. So if you see at the end, it's going to come as 0. Yeah. So the final answer is, you can cross verify also. I have done it in both the ways, solving the formula and then like substituting the values, or else substitute the value and then rearrange the equation as well. So the answer comes here as 9.2 gram per liter, which is option which is closest to option C, that is 9.5 gram per liter. You can do it by yourself once. Okay, moving to question 2. Just a minute. In a chemostat containing suspended cells operating at steady state with negligible death rate, which of the following statements is bar are valid? The specific growth rate of cells is equal to the dilution rate. The specific growth rate of cells is greater than the dilution rate. The specific growth rate of cells is lesser than the dilution rate. The specific growth rate is unaffected by dilution rate. Okay. So option D is not right, that we already know, because we already have understood that there is a relation between, in chemostat there is very strong relation between the specific growth rate of the cells to the dilution rate. Okay, we'll just see A, B or C, like whichever is like right. So consider a bioreactor like which is operating under continuous condition. So the inlet is going to be Fi, that is the flow rate, that is like the media that is getting inside, and Si is the initial substrate concentration, like whatever is like we are feeding, and what is the what Xi is the initial cell concentration that we are feeding from the cell recycle. Okay, whereas whatever is going outside, sorry, here I have given the arrow mark in the wrong direction, it should be out of here. So the flow rate, that is outlet flow rate, and the substrate concentration in the outlet, as well as cell concentration at the outlet. Okay, mass balance on cells. So the overall mass balance is Ra minus R naught plus Rg minus Rc is equal to d by dt of M. So this is what the overall mass balance that we use. Okay, so here we know that what to say, there is no outlet of cells are there, but we are not feeding any cells inside because we didn't talk about recycle at all. So how it's going to be, your Ra is going to be 0, whereas if there is any consumption, no, because they have already given there is negligible death rate. Okay, your Rc and Ra is 0, therefore minus R naught plus Rg is equal to 0, because in what to say, your chemostat, it maintains steady state conditions. Therefore there will not be any accumulation of cells, that is your cell concentration throughout your chemostat will be the same, therefore the accumulation part will also become 0. So R naught is equal to Rg, this is what is there. So we will just try to substitute values for your generation as well as the outlet. If you see for generation, so generation is nothing but it corresponds to the cell replication, right? So that's why mu into x, whatever the specific growth rate is there, into the concentration of the cells, into the total volume, that gives rise to the generation of cells, right? Rate of generation of cells. It's not only the generation of cells. Whereas outlet, if you see the rate of outlet of the cells around this point, so it's dependent on what flow rate the cell concentrations are being removed, right? So the cell concentration corresponds to X, and the flow rate that it takes is into F. Okay. So if we just rearrange it, X and X will get cancelled. So X and X gets cancelled, and mu is equal to F by V, which is nothing but your I guess huh, X can be 0, and what is the other possibility? Mu is equal to D. Okay, so specific growth rate of cells is equal to the dilution rate. Option A is the right answer. Moving on to question 3. If E. coli is grown on a media containing both glucose and lactose, which of the following phenomenon is observed in its growth? So, if two carbon sources are given on the media, what is the phenomena that is being observed? Option A, dioxy growth. Option B, immortality. Option C, decreased cell growth compared to the use of only lactose as the carbon source, and prolonged lag phase. Okay, so this we have already, this might be easy for people, because if two carbon sources are there, what happens, the organism will try to utilize the source that is very easy for that to grow, whereas once that carbon source is over, then it will shift to the second carbon source that is present in the media. So this phenomena we call it as dioxy growth. Okay, so first it will try to utilize glucose because that is the preferred media, and once the glucose concentration goes negligible, like when it reaches like 0, lactose will only be available for the organism to take. If the lactose consuming genes are already present in the organism, it can utilize lactose, but only upon the complete exhaustion of glucose. So that's what I want to mean. So when it is going to change the carbon source, obviously it will get adapted, that will be the second lag phase, and then again its exponential phase comes in. So the answer is dioxy growth. But there is one more molecular mechanism that happens along with this that I wanted to explain you guys. Say for example, so this is the LAC-I promoter, that is the inhibitor promoter. Whereas these are the LAC-Z, LAC-Y and LAC-A are the genes that are involved in the metabolism of lactose. Okay, so what happens is that when glucose and lactose both are present in the media, whenever glucose concentration is high in the media, what happens is that the CAMP concentration will be very less. Okay, if CAMP concentration is very less, obviously the CAMP and CAP complex will also be very less. Okay, so this CAMP CAP complex acts as a activator for these genes like LAC-Z, LAC-Y, and this operon is there, right? LAC operon. For this to get activated, like this CAMP CAP complex is very very important. If it is not going to go and bind to this, very less expression will happen. So this expression will not happen at all. Okay, whereas when the lactose concentration is very high in the media, in the absence of glucose, when there is no glucose present in the media, but yes, lactose is present in the media, what happens is that, as I told, there is this what to say, inverse relationship between glucose and CAMP. Now glucose is not at all present in the media, so it's obvious that the CAMP concentration will be very high. So if the CAMP concentration is very high, what happens, this CAMP cap complex will also be very high. This will go and bind to your promoter regions or the upstream regions of the operon. So what happens is that the DNA polymerase will come and bind. So this acts as an activator. It will come and bind to the promoter, and the transcription happens, and hence the translation. Therefore, the lactose is going to get metabolized by the lac genes that are like going to get translated. Okay, so I just want to give you this knowledge also, not only regarding bioprocess. There is a molecular mechanism which shows that how this prioritizing the substrate happens when it comes to in the bioprocess. So question 4, at which phase of cell growth is the maximum specific growth rate observed? A, lag phase, B, exponential phase, C, stationary phase, and D, production phase. So we will see, like as we already know that, we will see, like I myself will try to explain you guys. So we'll just try to take a look on the growth phase. Okay, growth curve, lag phase, and your exponential phase sneaks in, and your stationary phase and death phase, right? Yeah. So in lag phase, what happens? The cell will try to get adapt to the nutrients that are present in the media, because these are being given in a new environment also. So the in lag phase, what happens is that the cell tries to adapt to the nutrients in the media, okay, to the environment that has been given to the cells. So here what happens is that the cell size increases. It will start feeding on the substrate, very very negligible concentration it will start to utilize. But here what happens, the cell size increases but not the cell concentration. So here what happens, cell size increases but not the cell number. Therefore in lag phase, mu is equal to 0. Okay, and comes to the exponential phase where the cells grow exponentially. Okay, so here the maximum specific growth rate will be reached, that is equal to mu max. So once the exponential phase is also getting over, it reaches the stationary phase where your cell growth will also be there, your cell death will also start. Okay, but what happens is that here the rate of cell death and the rate of cell production, these are equivalent. That is rate of cell production is equal to the rate of cell death. Okay, so if you see at the end, there will not be any difference in the cell concentration at all. That's why this is a straight line. There will not be any change in the cell concentration, which means there is no cell death at all. It's not like that. So once it reaches here, still the cell maintenance as well as all the other process will be going, but it will be in a very minimal level compared to the like a log phase metabolism. Here the cell will be producing certain secondary metabolites that will be the main interest during the stationary phase. It What I wanted to mention here is that mu will be equal to 0 due to the rate of cell death as well as cell lifespan. And finally, we are going for the decline, like death phase. Okay. So, what they are asking, at which phase of the cell growth is the maximum specific growth rate observed? I have already answered where it is going to be in the exponential phase only. Moving on to question 5. What happens if the dilution rate is larger than critical dilution rate? So if your D critical is something that we have to operate at that only, right? You shouldn't cross that. What happens if the D that you are operating is greater than D critical? So that is what they are asking. Okay, wait, let me write. So critical is something that you shouldn't cross that boundary at all. So that's what they try to mean. It's a critical value that that we shouldn't cross that point. Okay, but here the question is, what happens if we cross? So we should know, right, what is the operating condition, like if we are crossing that, what happens? So option A, washout. Option B, higher growth rate. Option C, pH decreases. Option D, productivity increases. So here I feel like we can neglect option C, because the dilution increasing, surpassing the critical dilution rate and pH, I'm not very sure like whether it has any connection at all. Here we have to talk more about the cells only. Okay, because we know that D is equal to mu. So what is going to happen if we are like increasing D after like more than D critical? So either washout can happen, or it can like a higher growth rate can happen, or else like productivity increases. So we will see the equations for this. So we know that D is equal to F by V, right? So when D is greater than D critical, what happens is that you're almost increasing the yeah, here I have given the answer washout, but I'll explain like why I'm saying washout happens. So we know that D is equal to F by V. Okay, so if it's D critical, then F will be the critical flow rate, right? So it will be the critical flow rate. Here I'm just denoting it as F dot or F star. Okay, D critical is equal to F star divided by the total volume. Okay, so they are asking now, if I just operate it, what happens if F is greater than F critical? So what happens in chemostat? We are going to this is the chemostat where you're going to continuously feed the substrate, as well as you will be removing the broth at a certain flow rate, so that you can recycle the cells back, and then you can remove the what to say, fermentation. You will recycle the cells back, whereas like you will be keeping your media separately. Okay, if we are going to cross like if D is greater than D critical, what happens is that the flow rate has already surpassed the critical flow rate. So what happens, whatever the cells are there that are present in the media, so that will keep on coming, because of that washout happens. At a certain point, all the cells will come out only. Your steady state will not get maintained, nothing will get maintained. So increasing D more than D critical will go for will lead to washout of the cells. Question 6. Pseudomonas is cultured in the chemostat for the production of lipases. The chemostat has a capacity of 45 meter square. The substrate concentration in the continuous feed is 14 gram per liter. Ks for the organism is 0.51 gram per liter. Under the operating conditions, the organisms has a The organism has a maximum specific growth rate of 0.36 R inverse. Estimate the feed flow rate required to achieve 90% substrate conversion. Choose the answer closest to your calculated answer. So option A is 11.9 meter cube har inverse. Option B 15.61 meter cube har inverse. Option C 7.21 meter cube har inverse. Option D 21.2 meter cube har inverse. So sorry, one more time, I just wanted to read this question. Pseudomonas species is cultured in a chemostat for the production of lipases. Chemostat has a capacity of, so the volume that is given here is 45 meter cube. Substrate concentration in the continuous feed is 14 gram per liter. Okay, maybe the inlet, whatever is coming, that concentration is 14 gram per liter. K is for the organism, that is 0.51 gram per liter. And under the operating conditions, the maximum specific growth rate also they have given, that is 0.36 R inverse. We want 90% substrate conversion. So, okay. So, what should be the feed flow rate that we have to set it for this? Okay. So, we already so as we already told, P is equal to 45 meter cube, and whatever the concentration that is coming inside, Si is equal to 14 gram per liter, Ks that is 0.51 gram per liter, and maximum specific growth rate mu max is equal to 0.36 gram per liter, and like we need 90% substrate conversion. Okay, so what happens if we need 90% substrate conversion? Just a minute, let me draw. If we need 90% substrate conversion, 90% substrate should get utilized, and only how much should go outside? Only 10% should go outside. Okay. So if 10% has to go outside, we know 10% is nothing but 10 divided by 100, which is 0.1, into whatever the like 10% of whatever is coming outside, coming inside, right? So out of 0.1 into 14, that is equal to 1.4 gram per liter should only leave your chemostat. So this is what we are like guessing. Okay, so we need the remaining how much, 12.6 gram per liter to get completely utilized inside the cells. So what should be the feed flow rate for that? So to find the feed flow rate, we know the equation mu is equal to mu max is divided by Ks plus S. And we already know that in chemostat, like we already saw, right, in the previous, in which question we saw, I guess in question 2, I guess. I just want to show you guys before I proceed. Yeah. What we have seen in chemostat, the specific growth rate of the cells is equal to the dilution rate. So this is what we have derived and then we have understood here. So the same thing we are going to apply it in your next question also, like question number 6, I guess. Yeah. So we know that specific growth rate is equal to dilution rate. Okay. So D is equal to mu max into S divided by Ks plus S. As we already know, we know mu max, we know the substrate concentration as well as Ks. So we will be finding out the dilution rate. Okay. So substituting mu max is equal to 0.36 R inverse into the substrate concentration for the outlet is like 1.4 gram per liter, and the Ks is 0.51 plus 1.4 gram per liter. So D is equivalent to 0.264 R inverse. Okay, and we already know what, how D and flow rate are being connected. D is equal to F by V. Okay, so we already know the volume, that is almost like 45 meter cube. So multiplying that, that is equivalent to 11.88 meter cube R inverse. So that is equivalent to option A, 11.9 meter cube per hour. Question number 7, sulfide oxidation method can be used to roughly estimate volumetric, option A, volumetric mass transfer coefficient, then dissolved oxygen concentration, mass balance, option C, and option D is yield. Okay. So, what is sulfide oxidation method? So, if we see that, we'll just understand why we are doing that as well, right? So, in sulfide oxidation method, what happens is that you will be having a solution of sodium sulfite, that is Na2SO3, and oxygen will be completely like passed in the bioreactor, okay, in the presence of copper. So, in the presence of copper, oxygen and your sodium sulfite is going to get reacted to produce sodium sulfate, okay. So based on the amount, like based on how much conversion has happened from sulfite to sulfate, what can you understand? How much, for example, you have done the experiment at 200 rpm, 300 rpm, 400 rpm. So at 200 rpm, how much conversion has happened, and you can compare it with 400 rpm. So you will be understanding at a certain rpm, like your rpm as well as your what to say, the air flow rate, you would have gotten a very good conversion, for example 90% conversion, right? So that 90% conversion means what does it mean? Because it didn't happen in other aeration rate as well as other rpm, other combinations, it didn't happen. Whereas in a particular aeration, for example 3 liter per hour and then like 600 rpm, you have got 90% conversion from sulfite to sulfate. This means that your oxygen has reacted with your sodium sulfite very very good, which means the oxygen that has entered into the sodium sulfite solution was like properly broken by the impeller, as well as the what to say, the dissolved oxygen concentration would have been very high. That's why this had the like opportunity or the environment to get interacted with the sodium sulfite to transform into sodium sulfate, okay. So, what does that mean here is that obviously in more or the other way, it's going to talk about the KLA. Okay. So it's the volumetric mass transfer coefficient. If that is high, you will have a very good oxygen transfer rate. That's what is like. That's what I wanted to tell you guys from this one. Okay, whereas the dissolved oxygen mass balance and yield, those are not related to sulfate oxidation method. The whole purpose of using this is that with this conversion we can figure out like what can be the optimal rpm as well as the flow rate with which we'll have a very good what to say, your dissolved oxygen concentration. So if we have very good dissolved oxygen concentration, then your cells will be able to respirate very properly and do all the metabolism. To find out that this experiment was previously being used. Now many dynamic method and all is being used, but not this one, because in sodium sulfite there will not be any cells and all, right? As the cell concentration increases in your fermentation broth, there only your problem comes. For example, your cell growth curve is there. If you even keep 3 lpm of oxygen also and 600 rpm, it will be completely fine, okay, during the lag phase. Even during the early log phase also it will be fine. But if you go for high cell density cultivation and all, you will be in Pichia pastoris, easily they are like achieving like 300 400 gram per liter of cells. In that case, when you cross a certain concentration, sorry, 300 gram per liter, I wrongly told, like 300 OD, 400 OD and all they are achieving. Okay. So in that case, what happens is that as the cell concentration increases, that's where like all the cells will be competing for the oxygen that is getting dissolved in the fermentation broth. And as the cells are like increasing very rapidly, even the viscosity as well as the density of the fermentation broth also changes, okay. Because of which you will not be able to use this as the method to find out which is the what is the right rpm as well as flow rate that we can use so that we can achieve high volumetric mass transfer coefficient. Because in this case you really can't cultivate any cells, you really can't mimic a normal process, right? In the fermentation broth you are going to have 600 700 OD. Can you mimic the same in the sulfite solution? Will the cell survive also in the, if that is the case? Okay, that's why these methods are not being used like recently or currently it's not being used. This is how the process has been started at first. Question number 8. Identify the device used in aeration flow rate measurement in a bioreactor setup. Baffles, rotameters, RTD, and tachometer. So we'll just see each and every equipment like separately. This is a bioreactor in which aeration flow rate is very very important, because what to say, like some organisms are like very you have to maintain a critical oxygen concentration. Say for example, for some organisms you have to maintain at least 5% of oxygen concentration in the fermentation medium. For some organisms it will be even 20%, 30%. So dependent on the metabolism of the cells, the aeration flow rate will also be keep on changing. Okay, for example, if the organism needs 5%, and if that has to be maintained, what how we can maintain? Either we can increase the rpm, or else we can increase the air flow rate, or else we can shift it from air cylinder to the gas cylinder, oxygen cylinder. But anyway, like we will be mainly playing with the flow rate as well as the rpm after shifting even to oxygen cylinder also. So if that is the case, how will you measure like what is the flow rate? You have to keep on increasing, right? If it crosses a certain value also, that is not very good for the cells. It will create so much pressure inside the fermentation broth, and the pressure will start increasing. So we have to clearly know what flow rate that is being maintained in the bioreactor setup. So the first is baffle. Baffles are mainly for what reason? Like we have already seen all these things at the start of the course only. Baffles are mainly for to prevent vortexing. Say for example, you have a glass of water. So we have sorry for the disturbance. Like we have baffles. Baffles are mainly for the to prevent vortexing only. Whereas coming back to the question, like baffles are mainly to prevent vortexing. Say for example, you have a glass of water and a spoon. If you just try to mix the water very like fast, what happens? The baffles will try to prevent the what to say. In that case, you will get a whirlpool type, right? Whatever the media is like water is there, that will be keep on like becoming a whirlpool in the mid of the glass of water. If that shouldn't happen, because what to say, the cells will get stuck in the whirlpool. That is not good for any bioreactor conditions. So that is why vortex, which is being kept as a hindrance in the bioreactor, so that the whirlpool will not happen. Whirlpool is nothing but the vortexing only. Moving on to rotameter. Yes, rotameter is being used as a used for maintaining the flow rate of air only. Okay, whereas RTD is nothing but you will be getting to know what to say. It's a sorry, RTD is related to your temperature detection and all resistance of based. It's related to your temperature detection, whereas tachometer is mainly used to find how much power is being supplied. The motor is there, right? If it rotates in 600 rpm, how much wattage is being used for this and all. So that's what is being identified, rotameters. Okay. Question 9. Match the microbial categories in A with their optimal growth conditions in B. So thermophile, psychrophile, mesophile. In thermophile, what happens, as the name only suggests, that thermophiles are nothing but these grows at extreme like temperature conditions. Okay, say for example, it is going to be your like yeah 45 degree to 80 degree Celsius. So 45 degree to 80 degree Celsius is the like normal conditions that a thermophile can grow also. So psychrophiles are nothing but your the organisms that grows between 0 to 20 degrees Celsius are only psychrophiles. Okay, whereas mesophiles are nothing but that grows in the normal room temperature or something like 20 to 40 degrees Celsius. So the answer is B. Okay. Moving on to question 10. If the substrate concentration like S is far far greater than Ks, then which of the following is true according to Monod model? Organism grows at its maximum specific growth rate. The specific growth rate of the organism decreases. the specific growth rate of the organism doubles, the organism reaches stationary phase. Okay. So we know that mu is equal to mu max Ks by S. What happens if S is like very much greater than Ks? So Ks will be very small, right? And hence it will be neglected. So S and S will get cancelled, and then mu will be equivalent to mu max. So the organism grows at its maximum specific growth rate is the right answer. Okay. So if there is any questions, you guys can send an email to me. Like my email ID is already being like circulated. If there is any questions also, you can post it in the comments of the YouTube video session. So it will be very easy for me to clarify those doubts. So yeah. So with this, I want to end the session. Yeah. So it will be helpful. I hope this tutorial session will be helpful for you guys to solve the assignment 3 of BT 39 course. Okay. Thank you so much.